Hello friends, so let us continue our discussion on different creep mechanisms. So we were presenting or representing the creep behavior of the material in terms of, or the conventional sense in terms of the strain versus time. And in this representation we assume there are two factors or parameters that are constants, and those parameters are stress and temperature. Depending on these constant parameters, that is the combination of stress and temperature, the creep mechanism that governs the behavior of the material under this given condition varies. We saw two different types of creep mechanism in the previous lectures. So one of the creep mechanism was dislocation glide. So this particular creep mechanism is prevalent when the stress is relatively, the key word is relative here, is relatively high, or the temperature is relatively low. So again the temperature is relatively low. In this case the mechanism that is operational is the dislocation glide mechanism. The characteristic feature of this dislocation glide mechanism is there is an imbalance between strain hardening and recovery. So whatever effect of the stress is, that is dominant over the effect of temperature. So this effect of stress is dominant over the effect of temperature. When you want to talk in general terms, the effect of stress is referred to as the strain hardening, and the effect of temperature in general sense is referred to as the recovery. And during dislocation glide, the strain hardening is more dominant than the recovery, and the only role recovery plays in reducing the effect of strain hardening or the increase in the dislocation density that is introduced by the strain hardening is through the annihilation of dislocation, and this it does by increasing the mobility of the dislocation and activating the slip systems. So as opposed to dislocation glide, the other mechanism that is operational under definite combination of stress and temperature is the dislocation creep. So the first mechanism is the dislocation glide, and the second mechanism which we saw is the dislocation creep. So this dislocation creep, we observe this dislocation creep or this mechanism when both temperature and stress are average. So they are relatively average, or they are close to the conventional values that we use in order to arrive at this representative curve. When these values are close to that conventional values, then the mechanism that is operational is the dislocation creep mechanism. So this is dislocation here, DISL, so dislocation creep mechanism. So in the dislocation creep mechanism, there is a balance between the strain hardening and recovery. The effect of temperature is able to counteract the effect of stress, and the temperature is able to reduce the or considerably reduce the dislocation density or the increase of it through appropriate process, and that process is the combination of annihilation which is observed in the dislocation glide as well, and the other process that acts to the annihilation that is most prevalent in the dislocation creep mechanism is the rearrangement or polygonization. Now we saw for the rearrangement of the dislocation from say an horizontal arrangement to a vertical arrangement, thereby forming a grain boundary or rather a sub boundary that frees up a lot of space for the new dislocation to move, thereby enhancing the plasticity, requires a special type of movement of dislocation called climb. So the amount of rearrangement depends on the amount of climb. Now this climb is influenced by the vacancies, and we saw in the previous lecture two characteristic features of the vacancies govern this climb. So one is the number of vacancies, the other is the diffusivity of vacancies. The faster these vacancies are allowed to move and higher their numbers are, then the climb will also be much enhanced based on this, and then meaning this climb will translate to the formation of sub-boundaries, meaning you free up space for the maneuvering of the newly formed dislocation and enhance the plasticity. Now we arrived at a numerical expression for or related the different factors governing the dislocation creep mechanism. So in the dislocation creep mechanism, the factors that govern it includes the usual suspects, the usual characterizing features, that is the stress and the temperature, and along with the parameters that are associated with vacancies. So number of vacancies and diffusivity of vacancies. Since the number of vacancies is relatable to that of temperature, it is dependent on the temperature, then those two are rather dependent terms, and you can just get rid of the NV here, or the number of vacancies, and consider the T to be the independent term or the independent variable, and ultimately this is the expressions that you end up with. And this is the factors that govern the steady state strain rate under dislocation creep. Now we arrived at, or we expressed, or we related these two or these three terms to that of the strain rate in this manner. We had a proportionality constant, we had the diffusivity of vacancies, the shear modulus, and the thermal energy, along with the ratio of stress and the shear modulus to the power n. Now the reason why we include this is the shear modulus. The reason we include the shear modulus is because we want to non-dimensionalize the rule of stress, and that's the reason why we include it. Now this is a power relation, and the rate is now dependent on the nth power of sigma, that is the stress. Now this dV here, or diffusivity, can be expressed as the constant and the exponential relation between the activation energy and this term here. Now this is a constant, and this is the shear modulus of the material, which is also a constant, and the temperature and Boltzmann constants are always the same, or we assume the temperature is to be constant, and Boltzmann, again, the name indicates it's a constant. So you can rewrite this expression as dt, and then you can rewrite couple all these constants and write it as a bar sigma to the power n exponential activation energy by kappa T. So now if you get rid of all these terms and you want to relate or see how the stress influences the strain rate, so in this expression here you have the role of stress, you have the role of temperature, and when you express or want to relate the strain rate or the creep rate to that of the stress, it is of this relation. So we ended up the final segment of the previous lecture by plotting a curve that relates the creep rate or the steady state creep rate with the normalized stress. The normalized stress is the ratio of the stress and the shear modulus. We saw it comprises of three regions. So there is a first region, a second region, and a third region. So it comprises of three regions. In the first region here, this region is characterized by n is equal to 1, and the second region here is characterized by n is more or less equal to 5, and this region, that is a breakdown of power law. So this power law relation, that is no longer valid here, not valid in the breakdown region. So in the breakdown region, the power law does not exist. In the second region, as the stress increases, the n becomes close to 5. In the initial stages, when the stress is a little bit comparable or it is low, then within the dislocation creep mechanism, within this mechanism, when the amount of stress is relatively low, then the n is equal to 1. So that means in this region, when n is equal to 1 in this region, the strain rate, the creep rate, is proportional to the stress, and this is often referred to as the Harper-Down creep. So the name is attributed to the people who identified this behavior first, and that's the reason when the n is equal to 1. It characterizes this specific region, and that is referred to as the Harper-Down creep. Now in this lecture, we will look into a new creep mechanism that is referred to as the diffusion creep. So this is the new mechanism that we will be looking at into in this lecture. The factors, the combination of the characterizing factors that introduces this creep mechanism is the combination of, again, relatively high temperature and low stress. So under this combination, what you would have is the diffusion creep mechanism that is operating during the creep behavior of the material. So it is characterized by relatively high temperature and low stress. Now, without going into the specifics of this creep mechanism, it is based on this condition. You could say that this is opposite to the dislocation glide mechanism. So this is in a position or in a state that is opposite to the dislocation glide mechanism. The dislocation glide mechanism, the stress was the dominant factor, or the influence of the stress was dominant. Here the influence of the temperature is going to be dominant. So in the dislocation glide, we had the strain hardening dominant over the recovery. Here the recovery would be dominant. The recovery or the effect of temperature would be dominant. Now let us try to understand what this diffusion creep mechanism is and how the temperature of how the effect of temperature presents itself. So in case of strain hardening, the way the strain hardening presents itself is through the increase in the dislocation density. So with respect to dislocation density, we can then explain or describe the different creep mechanisms. So we explained the creep mechanism in the preceding creep mechanism based on the increase in the dislocation density when it was concerned with the strain hardening. Now we will see how the pronounced effect or the dominant effect of the temperature presents itself. So one factor that directly relates to the temperature is the diffusivity of vacancies and the number of vacancies. Now these two factors are directly dependent on the temperature. So this factor here increases, the number of vacancies increases with the temperature, and also the diffusivity, because of the increase in thermal energy, also increases with the temperature. Now the equilibrium increase in one of these features is the number of vacancies. So the stable increase with respect to the temperature is the amount of or the number of vacancies. So the pronounced, or as the temperature gets more and more increased, or the temperature is increased, then the equilibrium or value of the vacancies also correspondingly increases. So this means when we write an expression, we have already written an expression for the number of vacancies that we relate to the overall number of components that are present to the temperature by this relation, where the kappa T is the thermal energy which involves the Boltzmann's constant, and EF is the energy required for the formation of vacancies. So EF is the energy required for the formation of vacancies. Therefore, with increase in temperature, the number of vacancies increases either just through the thermal energy or by reducing the energy required for the formation of vacancies. So there are two possibilities to that. Now, as the temperature increases, this term here becomes less and less possible because temperature is in the denominator. So this term here becomes less and less as the temperature increases because this T is in the denominator. Now, the introduction of stress also has an influence on the number of vacancies. So the introduction of stress also increases the number of vacancies. So this exclusive expression for the dependence of the number of vacancy and the stress is expressed as for a given temperature T, when you have a stress sigma acting on the material, then the number of vacancies increases with respect to the stress, and this is the expression for it. And the term here, this term here is nothing but the molar volume, local molar volume. Okay, so you now have the stress also influencing the number of vacancies, but at low temperatures, when the temperature is low, and under those conditions, the formation energy or the energy required for the formation of the vacancies is very much greater than that of the influence of the stress. So because under low temperature, this term is significantly, or the magnitude of this term is significantly higher than that of the influence of the stress, this contribution is ignored at the low temperature. However, when the temperature is increased, the range of these two terms at high temperature, the range of these two terms become comparable. So these two terms, the ranges of these two terms become comparable. Then at high temperature, you can no longer ignore the influence of stress on the number of vacancies. So at low temperature, you can ignore the influence of stress, because when compared to the energy required for the formation of vacancies, this contribution of stress is not sufficient enough. However, at high temperature, because the T is in the denominator and sufficiently the requirement of the formation of energy is reduced, the role or the contribution or the influence of the stress at high temperature becomes more pronounced when we talk about the number of vacancies. So therefore, at high temperature, this contribution or this influence of the stress in governing the number of vacancies should be included. At low temperature, this is ignored because the formation or the energy required for the formation of vacancy is considerably higher. So even if you introduce this term, it's not going to make any difference. But at high temperature, since we have T at the denominator and also sufficiently the energy required for the formation decreases, and in that case, this influence of stress becomes relatable to that of the energy required for the formation of vacancies, and in that case, under high temperature condition, then you cannot ignore the role of the stress in producing new vacancies. And therefore, at high temperature, the expression that combines the role of energy required for the formation of vacancies and the influence of stress, the combined expression looks like this: N minus EF plus, or rather we can write it as EF minus kappa T. So what essentially we see is the introduction of stress reduces the energy required for the formation of the vacancies. So as the temperature increases, the stress allows for the more number of vacancies to be formed by the reducing the energy required for the formation of stress. So this effect is always there, and at low temperature this effect is not much pronounced, but at high temperature it becomes more pronounced, because this combination here, this energy required for the formation of vacancies correspondingly decreases at high temperature, and thus the reason why this effect of stress in reducing the energy required for the formation of vacancies becomes more pronounced at high temperature. Now, instead of talking in terms of the number of vacancies and the total number of components, we can write this in terms of, say, mole fraction. So this would be exponential energy required for the formation of vacancies and the contribution of stress divided by kappa T, that is the thermal energy. So this here is the influence of stress in reducing the energy required for the formation of vacancies. Now, when you consider a system, say a single crystal system, and you are applying a stress in this direction, a tensile stress under a high temperature T. So this is happening at a relatively high temperature T. That means the diffusivity of the vacancies is also considerably enhanced. So this is more than the temperature that we have considered for the dislocation creep. What we are talking about is a new mechanism, that is the diffusion creep. The temperature here is considerably higher. Now, because of this high temperature, we have an effect of stress in the number of vacancies that are being produced at that temperature. So when under such condition you have a tensile stress of sigma acting in this direction, then there is a corresponding stress that is acting along this direction because of the Poisson's effect. So because of the Poisson's effect, you have a corresponding stress that is acting along the lateral direction. If we assume that the tensile stress and the stress that is synonymous to the compressive stress that is acting along the lateral direction, they are equal in magnitude, but just the signs are different. They are equal in magnitude, but just the signs are different. Then we can expand the expression here we have for the overall number of vacancies. So under such a condition, we can now calculate the number of vacancies that are produced for the tensile loading and the number of vacancies that are produced for the compressive loading. So what we are essentially thinking about is, we are thinking about a crystal or a sample wherein you are applying a tensile load, and because of the Poisson's effect, you have a compressive load that is acting along the lateral direction. So we have to introduce appropriate values here in order to calculate the number of vacancies produced with respect to the tensile loading and the compressive loading. We assume that the magnitude of the tensile loading and the compressive loading is equal, only the direction or the directions vary. So that means by convention, the tensile load will assume a positive value, the compressive load will assume a negative value. Now let us try to find the number of vacancies that are produced by the compressive load and the number of vacancies that are produced by the resulting or the Poisson's effect caused by the tensile load. So we want to calculate, we want to calculate the number of vacancies that are produced by the imposed tensile load and the corresponding number of vacancies that is produced by the effect of or the Poisson's effect and the consequent compressive load. So let us try to substitute those values of stress. So let us begin by considering or writing an expression for the number of vacancies produced by the tensile load. The condition for which is, or the stress which is operating, is sigma. So that means it will look similar to this. It is C exponential term minus of EF minus sigma omega kappa T. So this is the expression for the number of vacancies produced by the tensile load. Now we want to know the number of vacancies produced by the compressive load, and it would look something like this. You write this as EF. Now here there will be a minus, but given the convention the compressive load is acting, then by convention you have minus sigma and omega, this divided by the thermal energy. So this would be the expression for the number of vacancies introduced by the compressive stress, and if you rewrite this, you would end up with an expression that looks something like this, plus sigma omega kappa T. Now what we observe is, while the tensile loading is reducing the energy required for the formation of vacancies, the compressive loading here, it increases the energy required for the formation of vacancies. So that means even though the magnitude of the stresses are equal, because of their nature of the stresses, one is tensile, the other is compressive, there is a significant difference between the vacancies that are produced, the number of vacancies that are produced by the tensile loading and the number of vacancies that are produced by the compressive loading. So let me repeat what we have done so far. So what we have essentially done is, we have observed that as the temperature increases, the effect of stress in governing the number of vacancies becomes pronounced. So we have an expression for it, we have written it down, the common expression, we have written it down here. Now we consider a system that is similar to one we have during the creep testing. There is a tensile load applied to it, and we are holding that material for a definite period of time, and the load is applying on it. Under that condition, because of the Poisson's effect, you have a compressive load that is acting along the lateral direction. So in that case, we need to substitute appropriate stress values in this generalized expression. So when you assume that the magnitude of the tensile stress and the compressive stress are equal, only the direction varies, then the number of vacancies produced by the tensile stress is expressed by this relation, and the number of vacancies produced by the compressive stress is expressed by this relation. And it is evident that while the tensile load reduces the energy required for the formation of vacancies, the compressive load or compressive stress increases the energy required for the formation of vacancies. So that means there will be a considerable difference between the vacancies that are formed because of the tensile load to the vacancies that are formed because of this compressive load. So the vacancies that are formed because of the tensile load and the vacancies that are formed, the number of vacancies that are formed because of the tensile load, CVT will not be equal to that of the CVT will not be equal to that of the CVC, and considering that the compressive load increases the energy required for the formation of vacancies, it means CVT will be greater than that of CVC. This is number of vacancies formed because of tensile loading, number of vacancies because of compressive loading. So now we can find the difference in the number of vacancies because of the compressive and the tensile loading. So let that difference be referred to as the delta CV. This is nothing but CVT minus CVC. So we know the expression for CVT, and substituting those expression, it is nothing but CEXP minus of the energy required for the formation of vacancies minus the reduction of it in it because of the stress contribution. So we have this term here minus CEXP minus of the energy required for the formation of vacancies plus the compressive stress and capacity term here. So you can even further expand this and write it as C exponential term minus EF by kappa T, or rather you can simply write it as EF by kappa T, and then you bring this minus inside, that would mean at exponential by the contribution of the stress, and similarly you can write this term as minus C EXP minus EF, that is the energy required for the formation of vacancies, and EXP. So you bring this minus here, that would mean by kappa T. So you have extended this to and you now have an expression for this. Now the one other thing that can be done is you can bring this minus out, and you can then take all these terms. So you can, when you bring this minus out, this minus becomes plus. So ultimately the expression that you have would be 2C exponential. When you bring this minus which is here, you can bring this out and this term becomes plus. When you bring this to here, this term becomes plus, and then ultimately you will end up having an expression that looks something like this. So ultimately the difference in the concentration of vacancies that is brought about by the tensile and the compressive loading. So the difference in the concentration of the vacancies that is brought about by the tensile and compressive loading is twice of this expression EF kappa T and this term here. So now this term here, that is the combination of the stress and the molar volume, when you compare to that of the the thermal energy that is introduced by the temperature, the relation between these two is something like this, meaning that the combination of the stress and the molar volume, when you compare to the Boltzmann constant and the temperature, which is nothing but the thermal energy or the introduction or the activation, rather the thermal energy that is introduced by the temperature, then its relation looks something like this, meaning the combination of stress and the molar volume is significantly less than that of the combination of Boltzmann constant and temperature. So that means you can get rid of the exponential term here, and you can write this expression as 2C, the energy required for the formation of vacancies, and kappa T, and the combination. So you can get rid of this exponential term here because of this relation here. That is because in a physical case, or generally speaking, you have that you have this relation, or the stress or the role of stress is significantly it's less when compared to that of the role of temperature. So you can write that as, you can in this case you can get rid of the exponential term or exponential relation and write them directly as this. So this term here is a constant for a given temperature. The energy required for the formation of a vacancy is constant for a given temperature, and this is again a constant. This is the total number of components, and the other term or the preceding term is 2. So the difference in the concentration of vacancies that is introduced by the tensile and the corresponding compressive loading because of the Poisson's effect is nothing but a constant multiplied by this here. So this is nothing but a constant and the role of stress. So the difference is purely introduced by the difference in the stress. So that is what we see in this expression. When you have the compressive loading, the amount of vacancies that are produced is reduced. When you have tensile loading, it is increased, and everything that happens is because of the stress that is being operated on the material, that is being imposed on the material. So correspondingly, the difference that you see in the concentration of vacancies is dependent on the stress. Now this is a difference in the concentration, that is the concentration in the vacancies that is brought about by the stress. Now we can find the gradient of the concentration by if we include the component of space into it. So meaning, if so far what we have considered is just there is a difference between the concentration that is introduced by the concentration of vacancy that is introduced by tension stress with respect to the concentration that is of vacancy that is introduced by the compressive stress. So we have found those expressions, we have taken the difference, and we have identified or quantified the difference in the concentration vacancies because of this difference in the loading condition. Now, since we have definite regions where these stresses operate, so we have definite regions. So this tensile stress operates in this region, and the compressive stress operates in this region. So it is possible for us to find the gradient across these 2 points. So gradient is nothing but difference in the concentration across a linear section. So let us consider a linear section of length L. So one point of that linear section is where the compressive load is acting. The other point of the linear section is where the tensile load is acting. We want to find the gradient in the concentration across this line L. So that can be done by just taking the ratio of this particular difference in the concentration of vacancies to that of the difference in the spatial positions that we are considering. So when you do that, it would be 1 by delta x. This delta x is the line we are considering, the different spatial positions that we are considering, and the different changes in the concentration accordingly. So it would look something like this. Part T. So A is a constant. So this constant is A. And now this we have considered it to be L. So this would be kappa T. So we now have an expression. So since this is a conventional way of representing the gradient, I have introduced the delta x here. So delta x is nothing but the line that we have considered, wherein at one point you have compressive load acting, at the other point you have tensile load that is acting, And because of the difference in the load, we have seen there is a difference in the concentration of vacancies, and we are relating this concentration of vacancies to that of the line that we have considered at two different extremes. And that is what we are doing here. By introducing this L, we are considering not just the difference, but the gradient in the concentration of vacancies. Now, the reason we want to consider the gradient in the concentration of vacancies is because, again, these vacancies are introduced by, or the difference in the concentration of vacancies is introduced by the difference in the mechanical conditions or the loading condition, and this is dominant, or this is comparable to the other values of energy of formation, because we are talking about high temperature. Only because we are talking about high temperature, or we are holding the material at high temperature, all these factors become relevant. That is, the role of stress in the vacancy, or the concentration of vacancy, is relevant only when you are talking about high temperature. When there is a role of stress in on the number of vacancies, then the nature of stress also influence the vacancies. Because of this nature of stresses, we have a difference in the concentration of vacancies, and that difference now we have translated it to the gradient. Now, the reason we have translated it to the gradient is because we want to consider the formulation of the flux of these vacancies, because the flux of the vacancies is what governs the climb, that rearranges the dislocation, and that enhances the plasticity. So for that, we need to consider the flux of the dislocations, and the flux of the dislocation is nothing but minus d, that is the diffusivity of the vacancies and its gradient. So the reason we calculated the gradient is because we want to calculate the flux of the vacancies, and the flux of this vacancies is given by this relation, which is nothing but Fick's first law. You have your diffusivity, or the diffusivity component here, that gives the mobility to the vacancies, and the gradient of the vacancies, which also add to the amount of flux, or the rate at which the driving force for the flux is governed by the gradient. And this gradient is introduced by the difference in the tensile, or the difference in the mechanical condition. So difference in the tensile and compressive load, we have this gradient here, and to that we have our diffusivity term, which is a constant, and there is a minus sign because of the way the flux moves, or the direction the flux moves. So now we have an expression for the flux of vacancies, and when you substitute these terms here, you would end up with an expression that looks like the flux of vacancies is nothing but 1 or minus d by L, and there is a constant A. So this d is the diffusivity of vacancies, so dV, and the factor that relates that introduces the stress in this expression. So now, the way one can relate the creep stress rate, or rather the steady state creep rate, to the flux of the vacancies is something like this. So in the case which we have considered, the way one can relate the steady state creep rate to that of the flux is something like this: 1 by L of GVR. So this is the way we can relate the steady state creep rate to that of the flux of vacancies. And now when you substitute this here, you could see that the steady state creep rate is dependent on 1 by L square dVA, the influence of the stress. So this is the final expression for the stress rate, or rather the creep rate under the diffusion creep mechanism. So this expression here governs the steady state creep rate under diffusion creep mechanism. So the fundamental factor that governs the diffusion creep mechanism is the difference in the concentration of vacancies. This difference in the concentration of vacancies is introduced because of the role of stress, and the role of stress in a given material, when there is a tensile load that is operating, you have, because of the Poisson's effect, you have a compressive load, and this difference in the signs of the mechanical condition brings about a difference in the concentration of vacancies, and because of this concentration of vacancies, difference in the concentration of vacancies, there exists a gradient We have simply considered a line over which there is a gradient that exists because of this difference in the mechanical condition. From that gradient, you can calculate the flux of vacancies, and from the flux of vacancies, you can relate the flux of vacancies to that of the creep rate that is observed during the diffusion creep. And when you relate this flux of vacancies to that of the creep rate, you end up with this expression. Now, it is important to note that similar to that of the initial stages of the dislocation creep mechanism, the one that we considered in the initial stages of this lecture, wherein the n was equal to 1. So, we saw in case of the dislocation creep mechanism, when n is equal to 1, you have your steady state creep rate proportional to the stress. Similarly, in case of dislocation creep, we have the similar relation as the, maybe I will highlight it with a different color, the steady state creep rate is proportional to that of the, or rather that of the stress here. However, this again depends on, this condition is not always prevalent because this moves to n more or less equal to 5 when you increase the stress, but here in the diffusion creep condition or in the diffusion creep mechanism as opposed to the dislocation creep mechanism, this relation always stands, that is the creep rate is proportional to the, is directly proportional to the stress when all these are constant. So this is what we saw it to be Harper-Down creep. So Harper-Down creep, wherein this is a form of dislocation creep characterized by n is equal to 1. This has a resemblance to the diffusion creep. So a specific form of dislocation creep referred to as the Harper-Down creep. So this is a D here, O, R, N. So Harper-Down creep is a form of a dislocation creep. It has its resemblance to that of the diffusion creep expression that we have arrived at here. So what largely characterizes the diffusion creep is that the influence of stress in the formation of or increase in the concentration of vacancies. So when you have a pronounced role of stress in the formation of vacancies, then you would end up with a mechanism that is referred to as the diffusion creep mechanism. So this diffusion creep mechanism is characterized by the influence of stress on the number of vacancies, and once there is a pronounced influence of stress on the number of vacancies, then what ultimately happens is, for a material that is under uniaxial tensile loading, there is a complementing compressive loading that is acting because of the Poisson's ratio. That means it would introduce a difference in the concentration of vacancies, and this difference in the concentration of vacancies would subsequently can be extended or related to the concentration gradient. So this will consequently introduce a concentration gradient in vacancies, and this concentration gradient of vacancies will then introduce or induce a flux of vacancies, and based on this flux, or this flux will directly influence the steady state creep rate, and that we have seen earlier. So from that we have derived at this expression here. So this expression, that is nothing but 1 by L square dV, that is the diffusivity of the vacancies, and the constant that relates all the other exponential term is nothing, and we have the role of stress. So what we have is, we have a constant, another constant. This of course is a constant as it relates to the exponential of the energy required for the formation of vacancies and temperature, and the variable here is the stress. And we have seen that this can be related to the one form of the dislocation creep mechanism. Now this vacancy here is the, or this term here is the diffusivity of vacancies. Now you can write this in different ways, in the sense you can separate how the vacancies diffuses. meaning you can write this term in two ways. Supposing in case 1, say you have two cases. In case 1, the diffusivity of vacancies occur largely within the grain. So you have a grain and the vacancies of the diffusivity or the diffusion of vacancies occur largely within the grain, then your diffusivity of the vacancies would be equal to the diffusivity of the vacancy within the grain, or the bulk diffusivity. So you have a case wherein the diffusivities or the diffusion of vacancies occur within the grain. There is not much way that the vacancies diffuse. Then the expression would be written as, you substitute this here, 1 by L square dV bulk, the constant terms here. So what we have essentially done is, we have made this particular creep rate, we related this particular creep rate to a specific form of diffusion, and that specific form of diffusion is the bulk diffusion, and we have considered the appropriate diffusivity there. So this form of diffusion and the creep rate that is associated with it is referred to as the Nabarro-Herring creep. Whenever you are talking about the diffusion creep, and exclusively you are considering the diffusion within the grain, within the bulk of the grain, within the bulk of the material, then you would use appropriate vacancy diffusivities, and then in that case the creep that you are studying, or the creep mechanism that it results in, is referred to as the Nabarro-Herring creep. So one characterizing feature or one distinguishing feature is just that we are replacing the overall diffusivity with the bulk diffusivity here in case of Nabarro-Herring creep. Now the other ways for the vacancies to diffuse is along the grain boundaries. Now in that case you would write the expression or make the expression specific to that diffusion. So in that case you would replace the bulk diffusivity with the grain boundary diffusivity, and all the other constants would remain, or all the other parameters would remain the same. When you change the diffusivities from the bulk diffusivity to the grain boundary diffusivity, it is referred to as the Coble creep. The overall framework of the expression that talks about the diffusion creep is the same. The only difference is we can vary the diffusivity terms, and depending on the diffusivity term you have different names for the diffusion creep. When the diffusivity term is associated with the bulk diffusion, we have Nabarro-Herring creep. When the diffusivity term is associated with the grain boundaries, we have Coble creep. Despite this difference, the overall expression, or the way this creep rate is related to, the stress and also the temperature is more or less the same in both these expressions, even in Nabarro-Herring creep and in Coble creep as well. In both these cases, it should be L square here. In both these cases, the way the creep rate is related to the stress and the temperature is the same. The relation of the stress and temperature to the creep rate is the same. So that characterizes the diffusion creep mechanism. The only change is that when you consider the bulk diffusivity, it is referred to as the Nabarro-Herring creep. When you consider the grain boundary diffusivity, it is referred to as the Coble creep. Apart from that, the overall expression, the relation to that of the stress and temperature is the same for the diffusion creep. Now the reference is the difference, the factor that brings about the difference between the grain boundary diffusion and the bulk diffusion is the activation energy. So you have your activation energy that governs the diffusivity in the bulk, and you have similar activation energy that governs the diffusivity in the grain boundaries. Now the difference is brought about by this activation energy because the activation energy along the grain boundary is less than that of the activation energy along the bulk, and this is the only factor that brings about the difference in the diffusivities, and correspondingly this is the only factor that brings about the difference in the Nabarro herring creep and the cobble creep. So in this lecture what we have seen is we have talked about a new form of a creep mechanism, and this creep mechanism is referred to as the diffusion creep mechanism. As the name suggests, the critical role here is played by the diffusion of vacancies. This diffusion of vacancies is caused by the effect of stress. The effect of stress introduces a difference in the concentration of vacancies. This is because when you apply a tensile load in one direction, there is a complementing compressive load along the other direction because of the Poisson's effect, and the influence of stress on the concentration of vacancies is dependent on the sign. So the tensile stress increases the concentration of vacancies, while the compressive stress decreases the concentration of vacancies. This difference brings about a gradient in the vacancies concentration. Once you have the gradient, according to the Fick's first law, you have a flux of vacancies, and because of the flux of vacancies, you can relate this flux of vacancies to that of the creep rate that we observe, and once you relate that, you will be able to get an expression something like this. You'll be able to get an expression something like this, and this expression is dependent on the diffusivity of vacancies. And when you consider two different diffusivities, one, the bulk diffusivity that occurs within the grain, the other is the grain boundary diffusivity. Depending on the diffusivity you consider, you have two different forms of creep within the diffusion creep mechanism. The Nabarro herring creep considers the bulk diffusivity alone, and the cobble creep considers the grain boundary diffusivity alone. So far what we have done is we have considered three forms of different creep mechanism, and we will in the next lecture we will see one more mechanism, and with that we will be winding up with the different forms of the creep mechanism. So we will see ourselves in the next lecture where we will be talking about one more creep mechanism. Take care.